Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so why don't we get started? Thank you for coming. I know it's very early in the morning, and I also know that there are buses arriving, I think, every 10 to 15 minutes. So hopefully we'll see, a few more people come in every 15 minutes or so. We also have a minor change of plans as far as the schedule is concerned. So we had originally planned to have 3 speakers here. Unfortunately, one couldn't make it. So George Candia from EPFL unfortunately couldn't make it due to illness. So, we considered what our options were. We wanted to maybe conduct a seance to, summon his spirits. We decided against that. So instead what we'll do is we'll actually change the schedule just a little bit. So we'll have Engin Kirde speaking for about a half hour, and I'll give a longer presentation on malware detection at Microsoft Research, which will go on for about an hour and will include videos and, fun little facts and things of that sort. So half an hour first, and then close to an hour towards the end, and I'll do the second talk. So many of you were at a keynote that Wolfram Schulte gave yesterday, I believe, right? Focusing on the work that's happening at RISE, Research and Software Engineering Group over in Redmond. And I'm actually one of the members of RISE as well. Clearly, one of the big themes at RISE is verification as well as bug detection. The theme for this session, is doing bug detection on a very large scale, in fact, a web scale. Both of the talks today will focus on topics of security. The first presentation is going to talk about finding vulnerabilities in the web application. The second is about malware. So this is my introduction. With this, I'm going to pass it over to Engin Kirde of the Northeastern University as of a few months ago. Before that, he worked in France, in fact. So, Engin.
Good morning. Does this work? Yeah, okay. All right, good morning, everybody. Thanks for coming to this talk. So the turnout isn't that high, so it's going to be a very personal talk. So I'll be talking about bug detection on a web scale, and I'll be specifically talking about some work that we recently did on detecting a specific class of vulnerabilities called parameter pollution vulnerabilities. So this is a new sort of vulnerability that was, that came out about a year ago. People were talking about this, and we were asking ourselves, how can we detect such bugs on the web automatically, and how prevalent are actually these bugs? So I will first give an introduction to this new class of injection vulnerabilities, which is called HPP parameter pollution. And what we've done is actually we've created techniques to detect these vulnerabilities. And one of my PhD students, Marco Balduzzi, actually came up with these ideas. I will then present a system that we built called PAPAS. It is an HPP detection system that can actually do a large-scale analysis of the web. So we can actually start this tool, go to websites, and automatically detect this class of vulnerability. This work was presented at NDSS in February, which is one of our good security conferences. And I will also present empirical results on the prevalence of HPP on the web. And I'll try to answer the question, how serious a problem is this really? So, as developers, do we have to be concerned about this? And what can we do to actually to detect and to prevent these bugs from happening? So the web as we know it has grown from a simple, very static infrastructure to a fully dynamic infrastructure where we have applications that are very, very interactive. So applications are actually more complex than they used to be, and web security over the years has actually increased in importance, and we have things like OWASP, organizations that try to help developers, that try to raise awareness in the community about web security and the importance of web security. Many complex systems have web interfaces today, and that's why it actually increases the importance of web security, because attacks against web applications actually constitute about 60% of the attacks on the internet today. So studies have been performed. Many of the attacks we're seeing on the internet actually target web applications because many critical applications have a web interface that can be attacked. Also, attackers may attack any site, any benign site, and then turn it into a command and control website that botnets use, or they might use it for launching drive-by download attacks that Ben will be talking about. A lot of work has been done to detect injection type flow. So you might have heard about SQL injection, a classic bug that is often found in web applications, but people have come out with solutions to detect such bugs. You might have heard about cross-site scripting, which actually is an attack where JavaScript or HTML is injected in an application. And it's a very simple attack, but it can cause big problems. So you might be cookie stealing, you might launch phishing attacks. And cross-site scripting is quite a big problem on the internet today. You have the classic parameter injection where parameters are injected into the application and the application can be compromised. So these classes of vulnerabilities have actually been quite well studied and quite a number of tools have been proposed and created in this domain. So we have things like stored procedures so that SQL injection bugs do not happen. We have sanitization routines in languages such as PHP that help developers to use them and to detect bugs, to prevent bugs. We have static code analysis systems. Some of them, for example, I worked on a tool called Pixie that can analyze source code and find these bugs automatically so that the developers can fix them. And we have a bunch of dynamic techniques that people have proposed in the past. So these can be also used to stop or to prevent these bugs from happening. So one thing we did in the past with respect to large-scale vulnerability detection was a tool called Secubat back in 2006. So at that time, we were wondering how easy would it be to actually scan the internet and to find, say, cross-site scripting bugs or SQL injection bugs randomly that can be exploited in practice. So we wanted to demonstrate how easy the attacker can find soft targets on the web if these vulnerabilities are not fixed. So we implemented a crawling engine for collecting potential targets, and we developed generic and automatically executable attack techniques to exploit bugs such as SQL injection and cross-site scripting. And we were looking into suitable analysis techniques. And we created this tool that was downloadable, and we actually tried it on the internet to see, are developers actually aware of these issues? And is cross-site scripting a big issue or not? That was back in 2006. So what the tool did was it prepares a new attack, and it actually sends it to a server. In this case, we were looking at client-side issues. The server sends back a response page. The analysis module parses the response and checking for the occurrence of the injected string and its executability. Basically, what we were doing was taking a piece of JavaScript, a very simple, benign piece of JavaScript code, trying to inject it into the application and looking at the response page. And if that script was in that response page, it actually meant that the JavaScript was not being filtered, meaning that something like cross-site scripting would be possible. So this was basically the architecture of the tool. So I'm not going to go into detail about that. The results were interesting because we actually crawled about 25,000 pages back then. We looked at about 20,000 web forms and looked at these 4 different attacks. SQL injection, a very simple form of cross-site scripting, a more enhanced form of cross-site scripting where you actually encode parameters so that filtering becomes more difficult. And we looked at things like form redirecting cross-site scripting attacks. And of the pages we looked at, and some of these were actually quite high-profile pages of companies that are well-known, SQL injection was still quite prevalent. So we had about more than 6% of the application's pages vulnerable to SQL injection. And cross-site scripting was comparable. So we had between 4 to 5% of the pages we analyzed being vulnerable to cross-site scripting. So that was about 5 years ago. Today, the situation is not much better. So if you actually run such tools again, you end up finding quite a number of cross-site scripting vulnerabilities. SQL injections have been going down. So there is improvement there, but things like cross-site scripting are still a big issue on the internet. So recently, we thought things like cross-site scripting have been well studied, but this class of bugs called HTTP parameter pollution was less known. So we were interested in this. It was actually presented by two guys, Di Paolo and Caratoni, at the OWASP conference in 2009. It had not received much attention, so we were thinking, okay, what if we look at this and try to find out how many % of the web pages out there are actually vulnerable to this type of problem. So the attack consists of injecting encoded query string delimiters into other existing parameters. It's a very simple attack. If the application does not sanitize the input, HPP can be used to launch client-side or server-side attacks against applications. So it's somehow similar to cross-site scripting. And the effect of the attack is that the attacker may be able to override existing parameter values and exploit variables that are actually out of direct reach. So basically, the attack consists of overwriting parameters that the application is using and overwriting them with other values. So the research objectives were, we created the first automated approach for detecting HPP flows. It was a black box approach, again, just like Secubat at the time. It consists of a set of tests and heuristics. So we wanted to find out how prevalent HPP problems were on the web. So this is the research problem we were interested in. And we wanted to find out if the problem was being exaggerated. So the first time I heard about this, I thought, this is very similar to cross-site scripting. I'm not sure this is a real problem. It just sounds like a very, very similar type of issue. We also wanted to know if this problem is known by developers. Does this problem occur more in smaller sites than larger sites, for example? And what is actually the significance of the problem? So these were like the research objectives we had. So to give you a very brief summary, we crawled the web and actually discovered that about 30% of popular websites are vulnerable to this type of flow, which is actually much, much higher than what we had seen with cross-site scripting or SQL injection back in 2006. So the problem seems to be very similar to the early days of cross-site scripting vulnerabilities where such issues were not known by developers. That's why everybody was, when they were writing code, they were making or building in such vulnerabilities. And developers seem to be largely unaware and protection mechanisms do not exist in most software. So we created a tool called PAPAS that is able to scan websites and report vulnerabilities. So I will briefly give you some details about this tool and how we actually detect these bugs automatically. So what is actually this HPP attack? During the interaction with web application, the client provides parameters such as get or post requests. So in this case, you might have a bank and it accepts two parameters, a login parameter and a session ID, say SSID, which is 1, 2, 3 in this very simple example. Special characters might be encoded in hex form. The problem is that if the parameter is provided twice, the language that you use to build this application determines which is returned back. So in this example, if I say the login is Joe and the login is also Kirda, so I provide this parameter twice to the application. If I use JSP, the first parameter is returned back to me, okay? And I have a list of languages here, so like ASP, PHP, JSP, Perl, Python. So depending on the language you use, when you want to get this parameter, the language actually determines, because of its implementation, which parameter is returned. So for example, in PHP, the last parameter is returned. So if I provide this parameter twice, Kirda would be returned back, Joe would be ignored, right? In JSP, the first parameter, Joe would be returned back, Kirda would be ignored. So depending on the language you're using, the behavior of the application changes. This is interesting in the sense that if you as a developer are not aware of this, and you have not thought about this, and you use different technologies or a combination of technologies, somebody can actually utilize this to do bad things. And this is the example that we're going to look at. So in a parameter pollution attack, it occurs when a malicious parameter, let's call it P injection, is preceded by an encoded query string delimiter, and it's injected into an existing parameter P host. So in a typical scenario, I'll give you that example, the user clicks on a prepared link, and the parameter is actually overwritten. So in this example, it's a very simple web application where I have, say, a voting application, and I'm asking for users to vote on candidates, okay? So in this case, there is a poll ID, and then I say the candidate is white. In this case, the candidate is green. So if my user clicks on this link, the application sends a vote for white. But if they click on this link, the application sends a vote for green. Okay? Very simple application. So how can you actually exploit this using HPP? If the attacker now creates this URL and says, poll ID is this, and then encodes this parameter right after the poll ID and says candidate is green, when the application parses this and builds these links, you get this output. So in this case, because the application is not expecting a parameter to be embedded in a parameter, when this whole thing is parsed, you get these two links, these two URLs. So if the developer relies on the language, the first parameter is always green, right? So whatever you click on now, because I've actually inserted these extra parameters into these URLs, whatever the user will click on will actually go to the candidate green, right? Very simple, simplistic example of an HPP attack. You embed a parameter into a parameter. So this is basically the problem, and there are many variants of that, and there are many more sophisticated things you can do with this. For example, there can be cross-channel pollution attacks. So HPP attacks can also be used to override parameters between different input channels. So I might accept something, a certain parameter, and override a parameter that I don't have no direct access to. So in the application, because of the application logic, I might just overwrite another parameter, for example. So a good security practice when developing web applications is to accept get and post parameters only from the input channel. But with cross-channel pollution, such protection techniques can be bypassed. HPP can also be used to bypass cross-site request forgery tokens. So this is one technique that web application developers often use to protect themselves against cross-site request forgery. Another class of attack where somebody can force the application to do something without the user knowing it. And just to summarize, HPP can be used to bypass these classes of protection mechanisms. For example, there was an attack against Yahoo Mail about a year ago, I think, where somebody was doing something similar like this. So basically, the architecture of the system is shown on this slide. So we have a database, we have a crawler. We crawl the web, and we have different components. We have a vScan component that looks, first we have a pscan component that checks for the parameter precedence. So we try to find out automatically when we inject a parameter or which parameter is actually chosen by the application. We have a vScan component where we have certain tests that tries to find out if a vulnerability actually exists in the application or not. And we have an instrumented browser. So the browser opens a web page, tries to automatically inject certain parameters into an existing application, and then tests to see if the attack has succeeded or not, or if there's a potential problem or not. So the instrumented browser fetches the web pages and renders the content. Why are we using a real browser? Because if you do not use a real browser, you don't know exactly how the page will be parsed. If you use a real browser, then you know exactly what the user will also see and what the application was intending to do. The crawler communicates with the browser, determines the URLs to visit, and the forms to submit. The crawler passes the extracted information to the components, the pscan and the vScan components that I talked about. So pscan determines the page behavior when two parameters are injected. So basically, you just provide two parameters and then try to see what the application does. The vScan component tests and attempts to verify that the site is vulnerable to HPP. So in a way, we had to come up with techniques to do this without really attacking the application. So by providing parameters, trying to measure how the application behaves and trying to see if this bug exists or not. So the pscan component analyzes a page to determine the precedence of parameters if multiple occurrences of the same parameter are injected into an application. So what we do is we take a parameter val1 and we generate a very similar parameter val2, and then we just provide it to the application. So the original URL in this case would be, say, these two parameters, 1 and 2 would be provided, but we provide another parameter with a new value, and then we provide the same parameter twice, right? So this is val1, and then we provide the same parameter with a different value, and then we try to determine by comparing the pages which parameter is actually given precedence to. So if page is equal to page 2, the second parameter would have precedence. If the page is equal to the first page, the first parameter would have precedence. So we try to compare and see how the application actually reacts. So this would be the first step. So in practice, this naive techniques does not work well, of course, because applications are very complex and they have a lot of dynamic content. They have, for example, publicity banners, RSS feeds, ads, etc. So we have to actually do pre-filtering to eliminate dynamic components, get rid of embedded content, applets, CSS style sheets, etc. So quite a bit of work went into optimizing this. We also have to remove all self-referencing URLs, as these change when the parameters are inserted. And then we perform different tests to determine similarity. So we get rid of all the dynamic content, and then we have several tests. For example, we have tests like identity test. If all the pages are equal, that means the parameter is actually considered to be ineffective. So the parameter has no effect on the application. We have a thing called base test that assumes that the stripping works perfectly, which is actually seldomly the case. We have a test called join test. So the join test checks the pages for indications that show that the two values of the parameters are combined together by the application. We have a thing called fuzzy test, where we have some similarity comparisons, and we use some algorithms for doing that, just to test how similar the applications are, and we have some threshold values, pages are, and we have some threshold values for that. So after we know which parameter is given precedence to, we use the vulnerability scan component for testing to see if the vulnerability occurs or not. Basically, we do this by providing a parameter and embedding it into another parameter. So for example, something like foo_bar, which is encoded in hex, and then we check to see if this foo_bar string is included inside the URLs of links or forms in the answer page. So vscan starts by extracting different lists of parameters in the URLs. We extract different parameters that are present in the page. So we basically get all the parameters. And then we have different groups. For example, the PA is the group of parameters that only appear in the URL. And in the links or forms of the page. PB contains URLs that do not appear in the page. For example, PC is a set of parameters that appear somewhere in the page, but that are not present in the URL. So we have different groups of lists that we have, and then we perform tests on these. Of course, there are special cases. I'm not going to go into that. For example, sometimes one of the URL parameters or part of it is used as the entire target of a link. This is often seen in pages that provide printing or sharing functionality. And to reduce false positives, we use some heuristics, so nothing is perfect. The injected parameter does not, for example, we check to see if the injected parameter does not start with the HTTP header. And using these heuristics, we can actually get rid of false positives as well. Briefly on the implementation, so we implemented this. It's a tool that's online. The components communicate using TCP/IP sockets. We support 3 modes. There's a fast mode, there's an extensive mode, there's an assisted mode. And the tool is actually quite customizable. So you can scan websites in depth. You can tune the number of performed injections. You can set page loading timeout. And you can do this on a web scale. So you can select 5,000 web pages, and you can actually go through them and try to see how many bugs you find. There are limitations. For example, we do not support the crawling of links that are embedded in active content, for example, Flash. And we only focus on client-side exploits where the user needs to click on a link. HPP is also possible on the server side, but first, this is more difficult to detect. And second, of course, you don't want to go into websites that you don't know and launch server-side attacks against them. Basically, that would be very problematic. We're looking at client-side issues. So measuring things is ethically, not a problem. Server side would be a problem because you would really attack applications. So this is actually analogous to detecting stored cross-site scripting, which is also a problem. So there are similarities with that. The evaluation, so that was the fun part to see how many bugs you can actually find on the web using this. So we conducted 2 sets of experiments. We used PAPAS to scan a set of popular websites to see if people are actually aware of this bug. We then analyzed some of the sites we identified to be, we thought we were having HPP in more detail to understand what was actually happening. So we selected the first 5,000 websites from the Alexa, from Alexa, and we had also sites such as Google, Symantec, VMware, Facebook, etc., all the big sites. And the aim was to quickly scan as many websites as possible and to see how common HPP flows actually are. So in 13 days, we scanned about 5,000 web pages. Of course, we did it very slowly. We don't want to, cause a lot of load. And more than 140,000 unique web pages, and we performed some tests on them. So we had different categories of web pages, for example, financial websites, games, government, health, internet, news, organization, scientific websites. Also social networking sites. So we tried to be as broad as possible. So we discovered that about more than 14,000 websites, that's about 30% of the total we analyzed, contained at least one page vulnerable to HPP parameter injection. And you also see the parameter precedence. So about more than 2,000 websites, for example, had the last parameter that was selected when we were injecting it. Some of them had the first, some of them were selecting both of them. In some cases, you could not determine which parameter had precedence. And if you look at the distribution of this bug across different classes of web pages, it's actually more or less uniform. So governmental web pages are as vulnerable to this type of problem as, say, financial institutions. So it seems to be a class of bugs that people are not really aware of, and that's why they're not really dealing with it. Also, we looked at some case studies. So we investigated some of the websites in a bit more detail. For example, also the Microsoft web pages. And in each case where we found a bug, we actually notified the security officers, and some of the problems were actually fixed. So this is one thing that is important to do. For example, in Facebook, there was a share component that was vulnerable to this type of bug, which has been fixed by now. And there were several shopping cart applications in certain websites that could be manipulated to change the price of an item using this type of a bug, for example. So some banks were vulnerable, so when you find a bug like that, of course, you don't play around with it, you just notify the people. And Google, for example, the search engine results could be manipulated. So these issues have been fixed. So in conclusion, I will just say that we thought this was an interesting class of bug, so we did an analysis on it. So we conducted a large-scale study of the internet. So this class of bugs seems to be not very well known by developers. And about 30% of the sites we looked at had vulnerable parameters, and about 14% could be exploited. This is much higher than what we were seeing in cross-site scripting, because this is a bug that developers are not aware of. So we're actually hoping that this work will raise awareness about HPP. And also the developers need to be educated and informed about this bug, because even if you use techniques such as static code analysis, if you don't understand the bug and if you don't need it, it's actually not that easy to fix. So with that, I'd like to conclude. If you have any questions, please feel free to ask. Thank you.
So we actually have a few minutes for questions, so please. Questions? Well, let me start with the question then. What kind of framework support do you think would be necessary, or for that matter, static analysis tool would be helpful for preventing these things in the first place?
It's a very good question. So with respect to static analysis, so when you do static analysis, usually you find out if there is a tainted parameter, right? So you need some sort of sanitization, but that's really difficult to understand or to implement without understanding the bug. So I think most important thing is education, so that people are aware of that, and probably maybe also some default sanitization routines, or some support with respect to in languages, so that if you have multiple parameters that are provided, at least maybe always the first parameter is returned or something. So something needs to be done and integrated into the language, I think.
Other questions from the floor? Come on, you must have questions. Don't be shy. Okay.
All right.
Well, let's switch over to the second presentation. Just give us a second here. This is on? Yeah. Okay. Sounds good. Okay, so let's get started. I'm happy to see a few more people here. I'm sure there are more buses arriving. I'm Ben Lefschitz. I work in the Redmond lab. I'm going to talk about malware detection on a very large scale. So this is a joint project that we started about a year and a half ago. What's interesting about this project is that we started it with basically very little, but some intuition about how attacks happen on the web, how large-scale drive-by attacks happen on the web. And from that point, we got to where we are now, which is a large-scale deployment with Bing. And so Bing is using the technology that originated from Microsoft Research to find thousands of malware sites on the web every single day. Okay, so first this. So brief history of memory-based exploits. And so this starts around 1995, in the dark ages of memory-based exploitation. What was happening was we had buff overruns, stack-based buff overruns, which is probably the simplest kind of these things you can find. There was some academic research done. Actually, before that, what brought interest to this topic is large-scale worms, things like NIMD and CodeRed. So after that, around the same time, I guess, there was some academic research being done. So one project in this space is called StackGuard. So the idea of StackGuard is that to prevent stack-based buff overruns, you can put these canaries to ensure some form of integrity of the stack. A relatively simple idea. Since then, it's been implemented in many compilers, like the Visual Studio compiler, for instance, has support for this very thing. And as a result of these developments, as a result of these compiler improvements in part, around 2002, we started seeing a new breed of memory-based exploits called heap-based buff overruns. So what's the difference between stack-based buff overruns and heap-based buff overruns? It's very simple, right? Instead of putting the payload, the malicious code, instead of putting that on the stack to be executed, the malicious code is actually placed on the heap, and then the attacker needs to figure out how to jump to that malicious code that is located on the heap. And so for a while, for a few years, attackers enjoyed sort of being able to exploit these kinds of problems. And then around 2004 or so, operating system vendors came up with technologies like that use randomization. So Windows Vista, starting with Vista, as well as Windows 7, obviously, has this technology called DEP and ASLR. And so the idea there is relatively simple. The idea there is that you randomize the placement of your heap within the process space so that as an attacker, you really don't know where to jump. So if you jump to a fixed location in the heap, you're likely going to miss and crash the program. And what happened around 2005, which is what prompted this research, and this is what I'm going to talk about primarily today, is this new brand of, new breed of vulnerability called heap sprays. I'm going to tell you what it is. I'm going to show some examples in just a second. Bear with me. What's interesting here is that there is this natural cadence between sort of an attack and a defense, right? Much of these defenses actually, interestingly enough in this space, do come from academia. It takes a few years for the industry to actually accept them and implement these defenses, but I think there is actually a lot of evidence that much of this academic research actually sticks and becomes sort of over time becomes standards, right? So there's this kind of attack defense kind of thing, and then for heap sprays, I'm going to talk about two projects that I've been working on called Nozzle and Zazzle. Crazy names. Bear with me for a second. I'll tell you where they're coming from. I think you'll see that. But before we do that, let me tell you about heap spraying. So heap spraying is something that's starting appearing in the news around 2005. By 2009, we actually started finding quite a large number of vulnerability reports talking about heap spraying. So this is a vulnerability report talking about Mozilla Firefox 3.5. Fairly recent, actually. So there was some vulnerability in the underlying software in the C++ that was possible to exploit using JavaScript. Here's another one. In this case, this is a vulnerability in the Adobe Acrobat Reader. So what they tell you, what's highlighted over here, is that we would highly recommend that you disable JavaScript in the Adobe Reader. Well, maybe as a temporary stopgap measure, that's not so bad, but really, in practice, you really want to have JavaScript support, in a product like that. So here's another one that talks about another, heap spraying vulnerability that uses ActionScript, which is a form of JavaScript in another Adobe product, another version of Adobe Reader. Here's something else that focuses, that targets, a version of IE and the vulnerable plugin that exists there, and so on and so forth. So what's interesting is the following. What's interesting is that we have complex products like browsers and, in this case, PDF readers and whatnot that are highly scriptable, right? In browser, you can really use JavaScript to do a great deal of work. I mean, that's how sophisticated applications like, Facebook and Hotmail work and appear interactive. But it also gives attackers immense power, as we'll see in just a second. So it's enough, oftentimes, to have a single vulnerability in the underlying product, like a vulnerability in the browser, for the attacker to be able to script around that and take advantage of that vulnerability. So how does one do that? So the next 30 seconds, I'll give you a very brief tutorial on how to create a heap spraying vulnerability. Use this knowledge wisely. So here's how you do it. You start with an empty blank HTML page. Nothing here so far. The first component we need is what's called shellcode. So basically the idea is that there is a string over there shown in blue. This is actually quite a long string. It goes for miles and miles. This is actually the malicious code that the attacker would like to be able to execute. Typically, what they want to do is install some sort of a service in your machine so that it would ping some sort of a botnet control type of setup, or otherwise exploit your machine. Maybe they'll want remote root, who knows what they want. But in JavaScript over here, we have this variable called shellcode that basically encodes this payload that will go onto the heap. Okay, so the second component of this attack is what's called the spray. So the idea here is actually fairly simple. So we take the shellcode that's allocated on the heap and create many, many copies of it all over the heap, right? This is the spraying aspect of heap spraying. How do we do that? Typically, they would use an array and then just allocate a whole bunch of these array elements, each of which is going to contain the shellcode. And then the last component over here is the trigger or the vulnerability, often called. And the idea here is that we really need to take advantage of some vulnerability in the underlying browser. In this case, the vulnerability actually comes from this add behavior call over here. Let me see if I have a pointer. Where is the pointer? No? Okay. Well, never mind. So this call over here, add behavior default user data, in fact exploits a vulnerability in all the versions of Internet Explorer 6. And they have this specially crafted parameter that basically leads to memory corruption in Internet Explorer. And if they do that carefully and skillfully, basically that leads to exploitation. So first they figure out what the payload needs to be, then they multiply it all over the heap, they spray the heap with that, and then they figure out a way to jump to the heap to actually execute that code. All right, 3 steps. And this is very typical. This is a relatively simple version, but actually we do find things that look very much like this in the wild. I mean, some of these attackers don't even bother changing variable names. So it's actually very apparent once you look at a piece of code like this that this is malware. I'll talk about two projects. One of them is a little bit older, called Nozzle. The other one is still ongoing, called Zazzle. So Nozzle is a runtime detector for heap spraying attacks. Okay? So as your browser is running, it observes what's going on and detects whether there is an attack that's happening. Zazzle is a mostly static detector. What it means is that we look at a piece of JavaScript code and we are able to tell with a very, very high probability whether it's benign or malicious. The next row in this column is the false positive rate. Now it's important to point out that if you have a static analysis tool, for instance, you might be satisfied with a false positive rate of, say, 10% or 5% is probably even considered pretty good. Or 1% is considered to be tremendous. At this pace, these false positive rates just won't fly. You have to have a tremendously low false positive rate to even get started. So why is that? It's because we want to be able to scan millions and millions of URLs out there. So if you have a false positive rate of 1%, we'll still flag thousands of them improperly, which will create a lot of chaos, essentially, and we want to avoid that. So what we have for Nozzle is a false positive rate that's close to 1 in a billion. 1 in a billion URLs that we scan, we mark as a false positive, mistakenly. For Zazzle, it's actually a little bit higher. It's about 1 in a quarter million to 1 in a million. We would like to actually lower that a little bit. But it gives you a sense of the kind of false positive rates you need to have to be able to find things on the web, as opposed to analyzing programs using static analysis tools, for instance. The reach, what is, how many things can we find with both Nozzle and Zazzle? So with Nozzle, as I mentioned before, we used Nozzle to find thousands of malicious sites on the web every single day with the help of Bing. Zazzle, we don't have as complete an evaluation at this point just yet, but our prediction is that we'll be able to go go beyond what Google can do with their safe browsing database. Okay, so let me just kind of briefly show this picture. So what I wanted to point out that this is an example of fairly academic research at MSR becoming part of a major product effort in a relatively short period of time of about 18 months. So I'll be the first one to tell you that tech transfer is far from easy, but in this case we had very nice and willing partners on the side of Bing, which is actually what largely made it possible. Not without a few kind of false attempts at first. We actually did approach a number of different groups and had some initial engagements with them before we found Bing as a very capable partner that allowed us to scale these ideas up. Because when we started, we really knew very little about this area. We knew that there were like 12 published vulnerability reports about heap spraying. That's actually all we knew. We really never knew whether we'd be able to find heap spraying attacks and other types of JavaScript malware in the wild at all. And lo and behold, every day now we are finding more and more. But back then we really didn't know any of this. Okay, so DriveBy Exploits, how does it work? Here's a scenario. So there's this character over here, the one with horns, and he has 3 machines, that's all he can afford, and he has a web document like the one I showed to you a few slides ago. That's all that he needs. And then we have an innocent user who goes to his site. Why does she go to his site? Well, we don't know. Maybe she gets a piece of spam email, who knows what's going on, but eventually she goes to his website. And then she gets out. This is called drive-by exploitation. It's great for the attacker. Why? Because all they need to do is they need to create traffic to their website, and then they'll be able to attack computers remotely. It's really quite an attractive scenario for the attacker. And that's why it's happening on a mass scale more and more. So heap spraying, what's the deal there? So if you have sort of an attack from a few years ago, maybe around 2005, this is what you might see, which is there would be a piece of HTML. This is a simplified version of what I showed to you a few slides ago that would have the shell code that looks like that, and as well as some sort of an exploit. So in this case, the exploit comes from overflowing the buffer that's allocated for the source parameter of the iframe. Okay? So the idea is that this shell code will become a bad object on the heap, And then by using that, by overflowing that source buffer, there would be a jump into the heap, right? That would hit that bad malicious object, and then will proceed to execute. So this is what was possible just a few years ago, before we had memory randomization. Now these attacks generally do not work. So instead of that, what one would do in the case of heap spraying, right? Because ASLR prevents this attack, is that they would use a piece of code like that, which is they would still have the shell code, which they would spray all over the heap, and there would be many of these bad objects allocated throughout the heap, and then they would jump into the heap. Jump into the heap at random, and chances are they'll hit one of the bad objects and proceed to execute the malicious payload. In practice, we find that they're actually very careful to spray the heap with a high density of these bad objects, so that their chances of hitting one of the bad objects is generally very high. So they're quite careful to basically, if they're doing this, they really want to be successful. That's really one of the morals of what we see out there in the wild. So this is the scenario. This is how heap spraying happens. What would we like to have? We would like to have some sort of a measurement device, a thermometer of some sort, that would allow us to tell whether a site is good or bad. Right? So if you have a benign site, it would say that, well, things are going well, I'm monitoring the situation, nothing funny is going on, keep on going. If I have, if I as a user go to a malicious site, I want this thermometer, this kind of measurement system, if you will, to tell me that something strange is starting to happen. And I want this system to react quite quickly, because otherwise bad things will have happened by the time I have a chance to react. So this over here is basically a cartoon. This is what we would like to have. Now on the right is actually real data we get with Nozzle. And so they essentially compare and contrast the two pictures, right? They look actually very similar. So let me just explain a couple of things. So the bluish line on the right is a benign website, in this case economist.com, the website for this magazine. The red line over there, the purple line over there, is one of the exploits that does heap spraying. Now on the y-axis we have this metric called the normalized attack surface, NAS, which is what Nozzle used to distinguish good sites from bad sites. I'll tell you how we build this metric. I'll tell you how that's constructed, but I think it's important to point out a few key observations here. First of all, it's actually a very robust measurement. In other words, there is a big difference between a benign site and a malicious site. There is very little confusion between the two. In fact, most of the time, this is exactly the picture we see. So the normalized attack surface for a benign site would generally be a few percentage points, maybe 5–6% at the most. Whereas for a malicious site, once it starts heap spraying, that metric, that value, the normalized attack surface, will generally go through the roof. It will approach 100% very quickly. And so the idea is that if you put a threshold around 70% or even 50% if you want, we'll be able to stop the program before it has a chance to do something malicious. So we have this clear separation between the benign and the malicious, and this is exactly what we wanted here. So before I give you any more technical details about Nozzle, I want to stop for a second and show you this movie. And the goal of this movie is to build up your intuition, because I don't know how many of you have taken popular sites out there and disassembled them. It's kind of a fun activity. Let me just show you this. That way we'll all be on the same page. So here's what's going on. This is Amazon.com. I'm actually using Chrome here to figure out what's going on underneath the hood. Why am I using Chrome? Because of its market share, it's actually not very likely to be attacked by malware. And so it's actually pretty good for malware disassembly. So here's what we're going to do. So let's see if I can play this video. OK. Yeah, there it is. OK, so this is, again, a benign page. Nothing, nothing funny going on here. I'm going to open the Chrome browser tools. Let me point out a few things to you. So in fact, it shows all the components of this page, including images and style sheets and things like that. Let me focus on the JavaScript, which is under the Scripts tab. First of all, there's about 0.5 MB of JavaScript code alone that's shipped to your browser when you go to Amazon.com. This is a great deal of code. This is, maybe 20,000, 30,000 lines of JavaScript code alone. So, and much of that code is actually very complex. So I think I am going to, well, maybe not, but some of it actually scrolled by. And the idea is that, if you're looking at that code, there's a lot of it. It's not clear what's going on. It's not clear whether it's benign or malicious. Okay, so far so good. Let's keep going. So here's another video. In this case, we're going to take a malicious site, I think. Okay, there you go. And this is a site that we found using Nozzle in Taiwan. This is some sort of a web store. We don't quite know what they're selling, but we think it's a web store because of the shopping cart over here on the left. There is, in fact, a phone number you can call. I really don't know what's going on, but it doesn't really matter. So I'm doing the same disassembly process here. Right? I'm looking at the tools, and I'm looking at the scripts, and this is what I'm finding. So when I focus on this one over here, this is what I see. So now look at that code. Does it remind you of anything? This is pretty much almost verbatim. It's the same malware code that I showed to you in the very beginning. So they're not even very embarrassed about calling their variables shellcode and payload and so on and so forth. So this is as kind of obvious a piece of malware as we generally find. Because of that, it actually makes for a nice example. Okay, so far so good. So hopefully this gives you some intuition about how these large websites are put together and what malware that's out there in the wild looks like. Back to some of the technical details. Okay, so let's think about it. So our goal is to detect heap sprays, right? So how does a heap spray work? It allocates a lot of this many copies of this malicious payload on the heap, just replicates it throughout the heap, and proceeds to force the program to jump to it. So maybe one idea is to actually look at the heap and try to see if it's executable. We allocate all these objects in the heap. Are they executable or not? So suppose we have two objects like that. Are they code or data? Right? So that's a natural question to ask. Can we even answer that question? Anybody knows? Code, data, both, anything, nothing? What's that? Neither.
Well, no, can't determine.
Can determine. Why not?
Well, you can try and execute it, that's all.
Okay, so you can actually try to execute it and you'll be very successful. Turns out that it's both, right? Turns out that just about anything you look at out there can in fact be parsed as x86 code because the x86 instruction set is so dense. So it turns out we've tried a whole number of things. We've tried a whole number of approaches. Some of them previously published, some of them we came up on our own. It turns out that none of the local approaches to trying to look at an object and figure out if it's code, if it's doing something malicious, really work. So what did we do? So before I tell you about that, let me give you a little bit more intuition. So generally what we see is the following pattern. Attackers create this NULL sled, a sled of no op or NULL instructions, followed by shellcode. This is a very typical structure that we see. So why is this what they do? Why do they do this? Anybody else? Yeah. Exactly. So let me just repeat that. So they cannot control where they're going to end up. They cannot control the target of their jump. So they want to basically increase the area where they can jump and essentially slide down to the beginning of the shellcode. If they had a huge piece of shellcode and just a tiny NULL sled, then chances are they would jump to the middle of shellcode and proceed to crash. So they want to regain control that has been removed from them through this randomization technique by creating this giant no-op sled. And this actually gives rise to an idea of how to detect these kinds of issues. So here's the idea in a nutshell. So we assume that the attacker wants to reach the shellcode no matter where within the object they land. Right? They jump into the object, they don't know where they're going to land, they still want to reach the shellcode. So we are going to take objects that are allocated by the program, generally speaking the browser, on the heap, on the operating system heap. We're going to disassemble those. We're going to construct control flow graphs for those. And then we're going to find basic blocks within the CFGs that are most likely to be reached through control flow. How are we going to do that? We are going to use data flow analysis, which is a traditional technique from compiler literature. So the strategy over here is that we are going to compute the surface area for each basic block. What is the surface area? Is the total number of essentially offsets or places within the object where you can land and eventually reach that basic block. And we are going to compute that value for every single basic block using data flow. So here's how it's going to happen. So we are going to start by giving the size of, by initializing the surface area with the size of each basic block. Right? Every basic block gets its own size initially, and then we are going to essentially push these values forward until we reach a fixed point. And let me just show you what the fixed point is. Turns out that that block on the right has a value of 15 because of everything that flows to it. There are some complications here that come from, for instance, some of these errors actually being impossible at runtime, so we actually remove them to avoid these false edges. But the basic idea, the basic takeaway here is that we find basic blocks that are most likely to be reached through this automatic process, and we do it very, very fast. Now, what do we do next? Oh, by the way, let me just point out something, which is this object over here that I use as an example is extracted from google.com. What does it mean? We go to google.com, there is a little bit of JavaScript code which allocates a few objects on the heap, maybe a few dozen, maybe a few hundred objects on the heap. Turns out that we basically go and take one of them and use it as an example. There is nothing malicious about google.com, the website, and we can actually easily take many of those objects and disassemble them exactly this way. This one is just small enough to fit in a slide. So here's how it works. We take the browser, using Nozzle, we instrument it to intercept its interactions with the, with the underlying operating system using Win32 API detouring, right? So every time it allocates memory or deallocates memory, we go and intercept that and basically do our own magic. So what is the magic? The magic basically kind of follows what I described before, which is we take an object, right? We proceed to build a control flow graph, a CFG. We compute the surface area or the thread of a single block. We maximize it over all the basic blocks within the object to compute the surface area of each object. Then we aggregate that across the entire heap to compute the surface area of the entire heap. And then we proceed to normalize it by the size of the heap. Okay? So this is kind of the full circle. Turns out that this is exactly what we want. So this is actually the value that we get, the normalized surface area, is a very good proxy for the probability of the heap being malicious. Okay? Great. So when we started this project, well, it's been more than a year now. We published in paper in Usenet Security, and we did a bunch of experiments that looked kind of like this. So we went to a number of these popular Alexa sites like Facebook and Hotmail and Gmail and so on and so forth. And we had a browser. We actually had IE as well as Firefox instrumented with Nozzle. We used both of them to make sure we don't find false positives. And Nozzle didn't find any false positives. We were happy about that. We also went through about 150 other sites automatically. Nozzle didn't find any false positives. We're really happy about that. And then we went look at for false negatives, which is we basically had a bunch of published exploits. Nozzle found all of them. We generated thousands more automatically. Nozzle found all of them as well. And then we looked at the runtime overhead. Initially, it was as high as 2x, which is really quite high. We started sampling objects in this Nozzle processing. We dropped it down to about 5 or 10%. This is what we did for the paper. Reviewers liked the paper. It got published. We were very happy about that. And then we kind of sort of stepped back and said, well, is this enough? And so this is where the difference between sort of, I guess, academic and slightly less academic research really emerges, which is this was a nice initial set of experiments, but that was only a start. There was tons and tons more work that went into actually making Nozzle practical, and I'll tell you about some of it. But it took us quite a while before Nozzle was deployed with Bing and was finding as much malware as it is today. And to recap, what we have now is, again, like I said, Nozzle finding, running on the server side in a data center with Bing, finding thousands of malicious websites daily. The false positive rate is tremendously low, so we had to do large-scale evaluations of that. We think it's close to 1 in a billion. I think in the last 6 months or so, I think we've only gotten 3 false positive reports. Each time we had to go back and investigate what was going on. Each time we figured it out. It took us some time. But 3 in 6 months is not so bad. Had it been like 30 or 300, our lives wouldn't be nearly as good. So, okay. And the other thing is that Bing's detection capability for malware detection went up twofold when Nozzle was enabled in production. So, okay. So what do we have? So we have Nozzle, which is this detector. And really, our initial ambition was to deploy Nozzle in a browser, right? We wanted to protect the end user. We wanted to create a browser like IE or a version of IE or even Firefox, for that matter, that would protect users from heap spraying exploits. That was, I think, a worthy goal, and I still think it is. But the problem really came from the overhead, right? So 5–10% overhead. So Usenet security reviewers thought it was, pretty great. They said, oh, it's less than 10%, something like that. Yeah, okay, super. We talked to our product people, and they were like, they were just kind of, well, at first they kind of refused to talk to us, but then, they talked to us, but they said, this is just a non-starter. Even if you had an overhead numbers maybe under 1%, maybe, but, this is just not, the kind of numbers that they were happy with at all. So we had an alternative plan. We had plan B, which was to basically use Nozzle on the server side in a data center to find malware out there, and then just kind of create these giant blacklists, which is what many companies do, right? So in the case of Bing, why do they want to have a giant blacklist of URLs? Because they don't want to serve malicious URLs to people who do searches. And so, in fact, if you do searches on Bing, sometimes you might see these URLs that are highlighted in red that say, well, go here at your own risk, right? I mean, I see these things quite a bit because I search for interesting things, but, you might see these things occasionally. The other thing is that browsers use blacklists of URLs as well. Actually all major browsers nowadays, IE, Firefox, Google Chrome, use blacklists of URLs. So the overhead wasn't good for in-browser deployment, but was actually pretty good for data center deployment. And that's what we did. And so instead of a single Nozzle machine, we have like thousands of them, hundreds of them. Great. And as a result of that, we started getting these giant feeds of data. So, several months ago, every morning I would come into work. There were like thousands of these URLs to look at. And obviously, there was really not much I could do manually. But, we really wanted to do something useful with this data. And we started thinking about what was possible. And really, our ambition was to create a static detector. And static detection has many advantages. One of them is very low overhead, right? There are other advantages I'll talk about in just a few minutes. So to recap, Nozzle observes the page as it runs. Watch for heap sprays. If there's a heap spray, kill that page, that process, or the entire browser. Maybe report about it to the browser manufacturer. That's the idea. Right? This is runtime detection. Zazzle, which is the follow-up on Nozzle, The original name actually means zero-day nozzle, but there is like a story I'm not going to tell here for why. Anyway, so, crazy names, but that's kind of how it is. So the idea with Zazzle is that we will examine the code before it runs. If we find it suspicious, if it looks malicious, there are two options. We can disallow, we can prevent the code from running. We can basically stop that page. Or we can enable a secondary detection capability like Nozzle, right? And so the idea is that instead of enabling Nozzle on every single page, it will only be enabled on a very, very tiny percentage of pages. So the actual overhead, right, the average overhead for the user will be very, very small. And they'll only pay the overhead price for things that might be malicious. So very clear sort of, incentive to actually structure it that way. Okay? So when we started to look at static detection of malware in JavaScript, the first problem that, that we hit was obfuscation. And obfuscation in JavaScript is just about everywhere you look. So here's, a bit of obfuscated code. And it's also kind of a programmer's joke. I mean, I think some of you can see that. But what's going on here is that, they're using these O's and L's to kind of stand for zeros and ones. And they're using this binary encoding to basically create this code and pass it to eval to execute code at runtime. Right? And then there is more and more code that emerges as you kind of proceed to execute this. So this is something that emerges, followed by that, which will produce that, and then eventually that, and it will produce this. So the idea here is that code unfolds itself. There is a lot of self-generating code in JavaScript, and sometimes it leads to malicious consequences. What's interesting, though, is that not all obfuscated code is malicious. There's plenty of benign code that is highly obfuscated. Right? So we, in the early days when we really didn't know this, we were pretty naive about this, we would like flag, what is it, ga.js. Google Analytics.js is actually quite highly obfuscated, but there is nothing malicious about it. So we really want to find things that are, obfuscated. I'm sorry, we want to find things that are malicious, despite the fact that they're being obfuscated. Well, how do we do that? Well, the observation here is very simple. Ultimately, the JavaScript engine, the JavaScript runtime needs to run the code. So ultimately, the code will pretty much unfold itself, and this is when we can capture it. So what we do is we basically sit at the entrance of the JavaScript runtime and capture all the code that goes through. Then what do we do with that code? Well, we write it out to disk, and then what we did is we built we essentially use some machine learning techniques, relatively simple machine learning techniques to build classifiers. So Zazzle is essentially a classifier that allows us to distinguish benign code from malicious code. Now, we wanted to be kind of principled about it. So what did we do? We did the following. So instead of just having kind of, treating code as text, as maybe machine learning people would perhaps do, we wanted to look at structured computer code. In this case, we wanted to look at abstract syntax trees, or ASTs. And our features were also hierarchical. So let me give you an example of that. So here's a piece of code over here. We would flag using Zazzle several features. So the first feature over here is this variable name shellcode. Another feature over here is the string towards the bottom. And then another feature is this variable called memory. What's interesting is that in this case, for the variable called memory, its context is the loop context. What does it mean? It means that when this variable is used within a surrounding loop, it will be matched as a feature. If this variable called memory appears standalone, it will not be used as a feature. So in other words, we use context in which things appear to increase the quality of matching, right? So to build a better quality classifier. And actually, this kind of stuff really pays off in practice, as we see. Okay. So this is how classification works, which is we basically start with giant piles of malicious code that we get from Nozzle, because nowadays we have thousands of samples, if that's what we want. We also get a whole bunch of benign code by crawling sites, benign sites like CNN and Economist and Microsoft.com and so forth. So there is no shortage of code out there to train on. Then we proceed to construct a classifier that we train on both benign and malicious samples. And the classifier, you know, we have quite a number of different classifiers, but in this case, this is naive Bayesian classifier that just has probabilities of different features that are multiplied together to get a probability of the entire code being malicious. So certain of these things have high probability of being malicious, like for instance, you know, function, a variable called shellcode has a very high probability of the entire thing being malicious. But something like if MSIE has a relatively low probability of being malicious because both benign code and malicious code uses that sort of behavior. Okay, so again, to emphasize, this is mostly static, which is to say that we unfold the code, right? We'll let the code unfold itself through the eval mechanism. And once it does so, we proceed to parse the code, create ASTs, and do static analysis on it. Okay. What's going on here? Okay. So what's the big picture here? The big picture here is kind of like this. So we have a whole bunch of these machines running Nozzle in a data center at Microsoft. And then we use these machines to basically distill a classifier. Right? And the classifier can be used in several different ways. We can use it offline, like we do with Nozzle, and we actually do that, some of that. Another option is to use it in the browser. So, you know, this classifier would be delivered to the browser and used for online detection as the user is browsing the page. And the nice thing about the way we construct the classifier is that it can in fact be integrated with the JavaScript parser. So at the same time as the JavaScript engine is parsing the incoming JavaScript code, it could also be sort of rating the code to figure out whether it's benign or malicious. And if it looks, you know, benign, it will just proceed to execute it without much of an overhead. If it looks malicious, it might do something different about it, like warn the user or stop it, or maybe enable other detection mechanisms. But the focus is on a very, very fast detection technique. Okay, back to the movies. So let's look at this. So I'm going to show you a highly obfuscated malicious page. So this page, koji.net, masquerades as msn.com from, I think, 2009. So this is actually one of the tricks that attackers use out there, which is they try to masquerade as well-known benign pages. Well, there you go. You can see December 2009 over there, see? And then New York on the right, and you can see what the temperature is. It's actually a static page. I mean, MSN clearly is dynamic, but this is a static page. You look underneath the hood, this is what you find. There's this file called jdefault that has quite a number of different snippets of JavaScript. So I'm highlighting the JavaScript for you to see, but the point here is that all of this JavaScript is highly obfuscated. And that's a problem. For me, as an analyst, it's actually very difficult to figure out what's going on in this code. And again, the fact that it's obfuscated doesn't mean that it's malicious. I cannot just say, well, I'll refuse to execute this code because it doesn't look good to me, it's not very readable. That's not going to fly, obviously, right? So I need to do something about it. So I'm actually getting desperate right around now because I cannot really, I mean, I don't even know where to start looking. I mean, look at this code and how much obfuscation they do. I'm going to paste this onto Notepad and show you a couple of things about that code. But the point is that, you know, it's really difficult to figure out what's happening. So there's like about a dozen different script blocks. And all of them eventually use eval, right? I mean, they basically construct their code on the fly out of these complicated looking strings. And again, the problem is that we don't know whether that code will emerge as benign or malicious. And that's the problem. So this is where I get stuck manually. Now let's bring some automation to this process. So I'm going to run Zazzle. And Zazzle is essentially going to automate what I did just now. It's going to go to that site, visit it in Internet Explorer. Okay, there it is, doing that. It will bring, you know, download images as well as JavaScript, all of that. I'm just not showing the Internet Explorer window because it's not very instructive anymore. But it's going to go and do analysis, and it's going to capture every single context, JavaScript execution context. And then the next thing we're going to do is that we're going to write the JavaScript out to disk. That's what that Python script does. And so there are about 20 different execution contexts, 22 different, I think, 23 different execution contexts that emerge as part of going to that page, right? So then I'm going to use Zazzle, the Zazzle classifier, to find which ones are malicious. And in this case, the Zazzle classifier comes back and says 20.js has a maliciousness score of 100%. So it's basically as malicious as it gets. And then I'm going to pretty print it and show it to you, and this is what it looks like. So lo and behold, this pretty much has all the signs of malware that we've seen before. It has a variable called scode that contains the shell code. It has a whole bunch of these different exploits that use ActiveX objects, instantiate Adobe PDF Reader, Java, applets, and so on and so forth. There's more shell code towards the bottom, depending on what kind of browser you use, and so on and so forth. There's spraying over there, and so on. So this is a very clear example of malware. But the idea is that out of those 23 contexts, only one of them was actually containing malware. And manually, it's virtually impossible to tell which one it is. It's only once you sort of unfold the code at runtime that you have a chance to automatically detect what's happening. And this is exactly what Zazzle does. Okay? So once we built Zazzle and trained it for a while, we wanted to evaluate how many false positives and false negatives it has. We started with a set of 10,000 benign URLs because our focus was on a very, very low false positive detection technique. Really, that's key for this kind of work. So in that set of 10,000 benign samples, we found 0 false positives. So what is the false positive rate? 0? It's less than 1 in 10,000 is what it is. I mean, assuming that some uniform distribution and so forth. Your visibility is limited by how many samples you apply it to, right? So we could say it's 0, but it's kind of disingenuous, right? Because, well, how do we know? It's like, having a telescope. There is, only so many stars you can see, right? There is a horizon that you reach. So what we did next is that we looked at a much bigger set of benign URLs, or URLs we thought were benign, of about 1.2 million. And this is the data that we get. So we start with 1.2 million samples. We find that Zazzle flags 9 of these scripts as malicious. We went and investigated these things by hand. Turns out that actually 5 of them, more than half, were in fact malicious. So Zazzle was actually doing the right thing, and people who created this golden data set were mistaken. We told them about it, but it was kind of interesting. 4 were false positives. So out of 1.2 million URLs, 4 of them were false positives. Now our numbers are actually slightly better still. We are decreasing the false positive rate, I should say, but this gives you a sense of what we are kind of finding out there. Now, what we want to do is we actually wanted to compare Zazzle to antivirus techniques. And what we find is that actually false positive rates are rather similar. So antivirus techniques, though, are traditionally very, very conservative. So it's typical for them to have tremendously low false positive rates, and Zazzle can match those. And I think that's actually very good, because Zazzle is very fast, can be built into a browser in a relatively simple way. And the other thing that's actually very interesting is that Zazzle has a very low false negative rate. So how do we assess false negative rates? We bring a whole bunch of these malicious URLs, make sure that Zazzle pretty much flags all of them. The false negative rate for Zazzle is less than 10%. For these 5 antivirus products listed on the right over here, it's actually generally quite high. For some of them, it's as high as 80%. So they miss 80% of these malicious scripts. Why? Because they want to be tremendously conservative. So I think what this slide illustrates here is that, well, several things really. First of all, Zazzle is highly usable, very precise, in that it has a very low false positive rate and a very low false negative rate. It also is a good illustration of doing research on a very large scale. Once you bring in a lot of data and start experimenting with it and looking at what comes out, you see some really interesting effects. We also wanted to do some experiments with both Nozzle and Zazzle, as well as Google Safe Browsing. And these are some preliminary numbers we are still working out, but this is kind of what it looks like. This is like a picture of, planets, right? This is like from an astronomy book or something, right? So in the middle, you see Zazzle. I'm sorry, in the middle, you see Nozzle, which is really quite small. It's like a drop in a much bigger bucket. To the left, you see Google Safe Browsing. And to the right, you see this giant, which is Zazzle. So in other words, Zazzle is able to detect considerably more malware than Nozzle, obviously. It pretty much includes the Nozzle circle. But it's also able to find more malware than Google Safe Browsing. I think part of it is the power of static detection, which is to say that malware doesn't have to execute for us to be able to flag it. That's a very powerful property, as it turns out, which is what allows us to find much more. See, there's a huge difference between, Nozzle and Zazzle, in part because Nozzle finds things at runtime. Malware actually has to run before Nozzle flags it. Zazzle doesn't care. Just looks at the code, looks bad, detect it, move on. So to recap, I've talked about 2 projects. Both of them focus on very large-scale malware detection. Nozzle is a runtime detector for heap spraying attacks. Zazzle is a mostly static detector for JavaScript malware. What's interesting is that lately we've been finding things that are not heap sprays, other types of JavaScript malware that are just emerging using Zazzle. Turns out that our training allows us to find things we actually haven't trained on, which is really very interesting. The false positive rate for Nozzle is about 1 in a billion. For Zazzle, it's getting close to 1 in a million. We're improving it still. Nozzle, finding thousands of URLs every day. Zazzle, I think, has a pretty bright future. We're still working on integration, and I think hopefully we'll have new numbers in that space in a few months. This is all I have. I'm happy to take questions. We have about 5 minutes left for questions. Yeah. We certainly would like that. There is certainly a gap between what one can see offline on the back end versus within the browser, and long term we'd like to see that happen. Yeah?
So what sort of strategies could malware writers use to try and defeat the classifiers?
Okay. So it's a traditional problem with classifiers, which is basically once you know what the classifier is, the malware writer can basically go out and spend some time defeating the classifier. And which is part of the reason why we don't actually publish the entire classifier. And we also have a quick feedback cycle, which is to say that we update these weights as well as the features. And we have a way to ship them, right? Ship these updates rapidly. But generally speaking, I mean, I think there are ways to write your code that would, clearly not using common variable names, like I showed before, would help them a lot. There are other techniques that involve runtime code generation that would allow to obfuscate things sort of to a point where we cannot sort of spot them as easily anymore. But again, in many ways, it's very difficult to design a sound detection technique that will find everything. But at the same time, finding things that actually affect people out there in the wild is what's tremendously important here. Was another hand? Other questions? Okay, sorry.
Yeah, do you have this is broadening the discussion a bit.
Yeah.
Great stuff. Do you have some sense of
This is broadening the discussion a little bit. So we have a fairly good idea of who some of the bad guys are. Most of them are people who are not very skilled, which is there's a great deal of copycat activities, which is why we can train these classifiers as well as we can, because much of the malware is actually just copied and slightly modified, is what we find. There are people, I mean, once we change our strategy, every once in a while we'd find people who are creative and interesting. They're clearly the minority. We have some statistics that we haven't yet published as to what the countries where this malware comes from are. Many of them are in Asia and Eastern Europe, which is fairly typical and generally meshes well with what antivirus company publish in this space. Beyond that, we haven't done analysis just yet.
You said that you looked at the countries where the malware is coming from. It doesn't actually mean that these guys are actually malware.
It's true. It's true. It might mean that it's easier for them to host it. That could be all it means. Yeah. You know, what's interesting is that there is also a fairly sort of flourishing industry for buying and selling these malware kits. So for about $40, I shouldn't be advertising this, but for about $40, one can go and buy, you know, this malware kit from, you know, a country in Eastern Europe, say, which will do, you know, some form of detection evasion, will be maybe even polymorphic and so on and so forth. Will do, you know, obfuscation and other things. Will bring, you know, 6 or 7 different exploits. Costs you, I think, about $40 with support if memory serves. It's you know, clearly, well, I don't know what to say about it. I guess one thing is that since they use these kits, it's also easy for us to train on these kits because we see so many samples, which also often renders these kits less effective than they would be otherwise. Okay, well, thank you very much. Have a nice break.